So welcome to the 15th edition of the live version of Physics Matter Colloquia series, prepared by the Forum of International Physics in the framework of Physics for Development program at the American Physical Society. So our live online event primarily targets Center of Excellence from our partner countries in the Sesame Light source, but also the observer country. And today we're going to travel to Switzerland. So we recall that our live science colloquia series is attracting a broad public, so ranging from early career scientists in developing community to anyone curious to learn more about our exciting scientific world. So where physics matter and where the value of collaboration can open new gates for developing community. So the broad span of our topic aims at reaching out diverse community and presenting societal challenge where physics can enlighten us and propose solutions. So don't hesitate to ask questions. So during the presentation, our guest speaker, so here will be happy to answer to that. And so we recall first that last September, Professor Vahid Karimipur presented an exciting topic of quantum information live from Tehran, so from Iran. And today we will dive more into the development in this field of quantum computer. So first I will introduce the member of our panel. So today, so we have first Joe Nimela, who is our chair of the FIP colloquium. And I'm Christine Dav, so coming from Switzerland, it's from Sweden, sorry, and I'm the chair elected of the FIP. And we have also with us, so Marilena Longobardi from Switzerland, so who is supporting the FIP newsletter. And today we are honored to have with us so Professor Dominik Zumbühl, so who is working now in Bâle University, but he get his diploma so from the ETH Zurich and his master at Stanford University. So Dominik received his PhD at Harvard University in 2004. He was working on the coherence in a spin on the quantum dots. After a brief postdoc in MIT, Dominik started his own group in 2006 at the University of Basel, where he has been working since then. So in 2008, he received an ERC starting grant. So in the first, this was the first ERC called. So after being promoted to associate professor in 2012, so he served as the chair of the department so from 2015 to 2019. And since 2021, so he is the director of the NCCR SPIN. So this is the Swiss National Program on Quantum Computing with silicon and the germanium spin. So Dominik's research interests are on the quantum transport experiment in semiconductor, nanostructure, focusing on quantum computation, so with spin, coherence, interaction, quantum condensed matter at ultra temperature, and machine learning for quantum device. So that's a very nice program that he will show us now. So I will leave the floor to you then, Dominik.
Thanks very much, Christine, for this extensive and very nice introduction. It's great to be given the opportunity to present here to the forum. And I'm just going to start sharing my slides. We tried this before, but maybe you can quickly confirm. Can you see the slides?
It works well. Thanks.
Great. Thanks very much. And as I think Christine already mentioned, please feel free to interrupt and ask questions also during the talk. If you have any questions, I will try to answer as good as I can. So today I will be talking to you about our efforts to build small, fast, and hot silicon spin qubits. And in particular, I will first give an introduction, and then I will tell you a little bit about our experiments in two different types of qubits. One of them is the germanium silicon core shell nanowire system, where we're looking at whole spin qubits, and the other one is the silicon thin field effect transistor, or FET, devices, which are also whole spin qubits. So quantum computing is one of the great challenges, I think, of today's time, And quantum computers, this is now quite well known, but I'll just make a short excursion into this. They are capable of solving a range of difficult hard problems. So hard problems means that today's computers would spend an excessively long time to actually solve these problems, or maybe they're not solvable at all. So of course, a quantum computer will take advantage of the laws of quantum mechanics and all the full possibilities, such as superposition and entanglement, that is at our disposal within the realm of quantum physics. And this can lead to an exponential speed up that leads to algorithms that can solve some of these difficult problems. So where would quantum computers be useful? Well, there's a whole range of possible applications. First of all, they would be very efficient at simulating other quantum problems. And this includes, for example, simulating and finding new molecules. Molecules are important for many different ranges. For example, in medicine, this could be important, but also across the chemical industry and pharmaceutical industry, there's many applications of molecules. With quantum computing, one could also try to find more efficient methods of synthesis of already known molecules, such as using less energy or consuming less raw materials in terms of resources. And yeah, these are some of the applications. Also, new materials could be found and simulated with quantum computers that could lead to, for example, in the area of green energy, new ways of converting one form of energy to another one, or for energy transmission or storage. So these are some of the applications that I just wanted to mention briefly. So today, quantum computers already exist. There are some kind of, toy model quantum computers that are running on just a few qubits. These are still not perfect, so they make errors, and it's now a big challenge to actually bring this ahead and push this to have more coherent qubits, to have them operate sufficiently fast, and also to scale ultimately to a much larger number of qubits. So there is a number of systems that are being considered, actually a surprisingly large different number of proposals that could be turned into qubits. And let me just here mention a few different ones. So the most well-known ones are probably the superconducting qubits and also trapped ions. And on those platforms, already systems exist with something like 100 qubits that can already do some kind of small algorithms, and they're even accessible through the web and the cloud and so on. And those are two of the, I would say, currently most advanced types of platforms for developing qubits. Then in silicon quantum dots, we can kind of make artificial atoms, and this will be much more explained in today's talk. And those are other potential qubits. Topological qubits, for physicists, this is of course a very exciting area of active research to find topological superconductors, Majorana fermions, even more complicated physical objects and excitations, which would be very interesting. And it turns out these can also be turned into qubits. Spins also in diamond, and in particular in vacancies and V centers, are also qubits. So the question is, what are their scaling properties? How large are these qubits? How fast are they? And so then there is quite a big difference between these qubits. So for the spins in semiconductors, these can basically be made on the scale of nanometers, and their operation speeds, I will show you in the next 45 minutes or so, can be up to the gigahertz range. So these can be characterized as small and fast. Now, the currently leading platforms with superconductors and ions, they are much, much bigger. So the typical superconducting qubit is hundreds of microns in size, and the operation speeds are more in the megahertz range, not in the gigahertz range. Trapped ions, of course, an ion on its own is not very large. It's a tiny, object, but to actually build a trap around it, it takes a considerable amount of space. And it's actually also, again, in the range of hundreds of microns, if not a millimeter. So these are quite large qubits, and it's easy to imagine how to integrate 1,000 or 100,000 of such qubits, but it's going to be very difficult to actually build 1 billion of them. It just takes a lot of space. The topological qubits, they're kind of more exotic, and in fact, it's not even clear today if they really exist. And moreover, since we don't know yet if they really have been successfully made in the laboratory, we don't know what their properties are. What's the relaxation time? What's the coherence time? It's not known yet. So these are kind of more explorative type of research. So how to build a quantum computer? Well, there is a recipe that we already have from over 20 years ago. David De Vincenzo came up with these 7 criteria that you've maybe heard of before. So what do you need to build a quantum computer? Well, first of all, you need a scalable system, something that you can make many qubits out of, not just a few, and they have to be well understood and characterized. Then it needs to be possible to initialize the quantum information into each and every of these qubits, and to basically, in this case, program the initial state in your set of gates. Then we need to be able to manipulate these qubits. And so we need to have a kind of universal control over each and every qubit, not only every single qubit, but also qubits need to be linked, and 2-qubit or multi-qubit gates need to be able to mate. And the coherence times of these qubits need to be long. And this is something to be, first of all, achieved for, the single qubit level, but then also when qubits are combined into larger assemblies, that still needs to be upheld, and the coherence needs to be still good enough. Then we need to be able to measure each qubit, to do the readout. I don't know whether that was marked first, but we need to do a readout also to again see what kind of the result is of the operations that we did. And then number 6 and 7, we need to basically be able to interconnect these qubits, which are typically stationary, for example, to photons or other kind of movable qubits, and transmit them between spaces for interlinking. And so in principle, if you look at the status quo of the state of the art of what we have today, we can basically check all of these boxes. But still, we don't yet have really like a fully universal quantum computer. And the problem is that the error rates that need to be achieved are just very stringent. So when we start executing algorithms, then after some relatively small number of steps, 100 or 1,000, basically the quantum information is lost due to the effects of decoherence and imperfect gate operations. So that's what's shown here. We're now basically, let me switch this here. Pointer, here we go. I hope you can see my laser pointer. We're now at the level of basically doing operations and algorithms on individual or a few qubits, but what we really need to achieve is error correction. So then we can actually start to make logical qubits. A logical qubit is a qubit that consists typically of several or even very many physical qubits, but it has implemented error correction. So that means this logical qubit would be basically infinitely long-lived, and you could then run your quantum computer with many of these logical qubits and run the algorithms on it. So in the superconducting community, there are some very exciting developments just these days. They've actually managed to implement some particular version of the surface code with 17 qubits. And that's a nice step in this direction. But unfortunately, it's the error correction is not yet good enough to actually overcome the effects of decoherence. So this error corrected qubit, it lives longer, but not much, and it still decays. So there is still a lot of work to do. So that's the kind of outlook that we have. And this is taken from a paper from 2013 from Michel Deboré and Rob Schulkopf. So now to give you a quick overview of the ecosystem. So this effort to build a quantum computer, this has basically become a worldwide, let's say, race. And there is a number of teams, laboratories, universities, companies, tech enterprises, and so on, startups as well, that have set out to go on this path. And so I will, of course, not be able to give you a complete list here. This is just giving you my personal impression of some of the important players. So on the superconducting qubits, that's this SC, we have the teams from UC Santa Barbara together with Google, who you've probably heard of in the news and in the media repeatedly, also from IBM. And these are running very ahead of basically the game with their superconducting qubits. And they are now making roadmaps for hundreds and thousands of qubits in the next few years. So that's very exciting. Another tech giant, Microsoft, has embarked on making qubits out of Majoranas, together with partners at Copenhagen, Delft, Purdue, Sydney, and other places. So as I've already pointed out, this is a bit more explorative, and they're trying to make a qubit. Then on the semiconductor spins, in particular in silicon, there is a few very noteworthy consortia that are working on this. In particular, Intel, one of the leading semiconductor manufacturers worldwide, has teamed up with the teams at Delft to work on the silicon spins. Grenoble also, together with Leti. Leti is still a full-scaling semiconductor foundry based in Grenoble as well. So they're right next to the university lab, and they're producing these wonderful, 300 millimeter wafers with transistors that they're now turning into quantum transistors in Grenoble. In Sydney also, they have a great project, and also a couple of startups and spin-offs that are building silicon-based quantum computers. Now here in Switzerland, since about 2 years, we have started a Swiss national effort in quantum computing with spins, and in silicon and germanium in particular. And this brings together the University of Basel with our groups here and many other groups in the department, together with the two ETH in Zurich and also in Lausanne. And our key partner, industrial partner, is IBM. So IBM worldwide, as you have seen, is of course working on superconducting qubits, but here in Switzerland, they have completely abandoned superconducting qubits, and they're working on spins together with us. And so, as I've said, there's many more, and actually it would be very interesting to see. There's many startups and many very well-founded companies that are also working on this effort. So this is an exciting time, and our particular effort is basically building on an idea that's now over 20 years old, almost 25 years, based on a proposal that came out in Physical Review A by Daniel Loss and David DiVincenzo. And the basic idea there is that the spin, for example, of an electron is an ideal qubit, because it's a natural two-level system. It's very stable, yet it is easy to manipulate it intentionally from the outside. And these spins can be hosted in what they draw this cartoon a long time ago in these kind of quantum dots that are made from semiconductors. Originally, the idea in this paper was to use 3-5 materials like gallium arsenide, indium arsenide, and such very well-established semiconductors in the research area. But of course, the challenge there is that they have nuclear spins. Gallium and both arsenic, they have nuclear spin 3/2. And that provides a path that leads to decoherence. So more recently, the switch has been made to column 4 materials such as silicon or germanium, which have a low natural abundance of nuclear spins of only a few percent, 5% or so of nuclear spin 1/2 in one of the isotopes in silicon or germanium. Okay. Now, what we are trying to take advantage here as well is, of course, the enormous development that the semiconductor industry has made over the past, I don't know, 50, 60, 70 years. So here is a photo from a wafer that came out from IBM about a year ago. And this is what they call the 2 nanometer technology. And this is the result of decades of intensive research in making these transistors smaller and integrating them. So you can have now a chip that's about a centimeter by a centimeter. It hosts something like tens of billions of transistors, and each of these transistors is only tens of nanometers in gate length, and they operate at several gigahertz speeds, dissipate an amazing amount of power, hundreds of watts typically. And that's actually one of the limits why these chips don't run at even higher frequencies. They would simply start dissipating too much heat, and they would start melting. And the cost, of course, of these semiconductor foundries is enormous, also in the billions of dollars. But then due to the huge market, it breaks down to relatively cheap prices of hundreds of euros or US dollars or Swiss francs. It's all about the same in value. So how was the scaling possible? Well, there is a number of technology, and I don't want to go through this, but I just want to point out the workhorse and the kind of most successful geometry for scaling is the so-called FinFET. I show it here. This is one particular scaling platform that over the past more than 10 years has really advanced the transistors to smaller and smaller sizes. So you have the kind of typical fin, that's this kind of tip looking structure here with then a gate that sort of wraps around it, and that provides for very good electrostatics due to this gate that tightly encloses a large part of the tip of the fin. You can turn on and off the currents flowing through this fin very efficiently. You get good on-off ratios, and that's what one needs for efficient transistors. And so that's what we also will try to take advantage of. So basically the idea is here to build on the shoulders of these giants from industry and to basically use the same technology that is today used to build our classical transistors in our everyday gadgets and computers, and to turn them into quantum bits. And so this is our Swiss national project here, which I will just have one slide to give you a quick overview and introduction to. So the objective here is to really develop fast, compact, and scalable electron and hole spin qubits. It turns out, of course, electrons have a natural spin 1/2. Hole spins also have advantages. I'll get a little bit more to that in just a few minutes. And so for this, we basically set up a research program. This is including the partners that I've already mentioned, the two ETHs, University of Basel as the home institution, together with IBM Research in Zurich. And this combines an interdisciplinary team that has quantum physicists, but also material scientists. The materials are of paramount importance in these qubit devices. We have engineers and computer scientists as well working together with the theoretical and experimental physicists. So with that now, I would kind of turn to the actual qubits and tell you a little bit about our experiments and our path in the last few years to build hole spin qubits out of these nanostructures. So why would you want to use a hole spin? There's pros, and the advantages of the hole spins are that they come endowed with the spin-orbit interaction. So it turns out that the electrons in the conduction band, they have the angular momentum quantum number L equals 0. These are the states that they're built out of from the constituent atoms. But in the valence band, these states have angular momentum L equals 1. And so there is intrinsically for these states here in the valence band a strong kind of spin-orbit coupling, because you get this L dot S type of coupling. And so the band structure is slightly more complex. You see there is 3 hole bands, whereas there's only 1 typically conduction band for these semiconductors. And this split off band here is usually not very important. And then here we have this heavy hole with the lower curvature and light hole with the higher curvature bands, which actually are degenerate in bulk materials. But then if you confine it in a quantum well or even a smaller 1-dimensional or 0-dimensional structure, then the degeneracy is lifted. And so the idea here is to actually use this spin-orbit coupling for all electrical manipulation. So if you didn't do this, then you'd have to use kind of an antenna, a strip line, where enormous currents would have to be pushed through in order to produce the time-dependent magnetic field. Technologically, that's very difficult, particularly since all of these experiments need to be done at Kelvin or even millikelvin temperatures, where we cannot absorb a lot of heat due to the lack of cooling power and poor thermalization. So here we don't need to use these high current antennas. We don't need to use micromagnets with the holes. You can simply enjoy if you wish, in a sense, the effects of relativity. So if you're moving an electron or a hole in presence of a static electric field, then if you transform to the rest frame of this electron, then due to the spin-orbit coupling, if you move this electron or hole back and forth along, let's say, some axis, then in the rest frame of this moving charge, you get actually a time-dependent magnetic field. And this is due to the spin-orbit coupling. So if you have motion in real space in the orbit, then you get action on the spin. And that's what we're taking care of here, we're taking advantage of. And the stronger this effect is, then the more quickly you could manipulate this spin. Oh, I see a question in the chat. Let me look into this. Oh, okay, not for me. Never mind. So that's what we're trying to use. We're basically shaking around our charges in our nanostructures with electric fields, which we can very easily apply at, let's say, gigahertz frequencies. And due to this gigahertz motion and the spin-orbit coupling, which is existing for the whole for the holes here very strongly, then we can get very efficient spin manipulation. So-called electric dipole spin resonance is what the technical term is for this effect. Now, what's a blessing is also a curse. In principle, if you have now a substrate which has also charge noise due to switchers, 1/f type of telegraph noise, then this noise will also couple to the spin. So that's the price that we will then have to pay. Now, the Hall spins also make the promise of having weaker decoherence due to the nuclear spins in the host material. And in particular, the electron wave function has, due to its S-type nature, the weight directly on the nucleus, and so has a strong Fermi contact hyperfine interaction. The holes, on the contrary, shown down here in the blue range, they actually are p-type wave functions. And so they have a node, a minimum, on the nucleus. And so there is no Fermi contact hyperfine interaction for the holes. And so due to the absence of this contact interaction, one can expect a longer hyperfine coherence. And now if we go to the kind of holes in quantum dot type of structures, what's of particular interest, and this is coming from a prediction by our colleagues in theory, Christoph Kleffel and Elena Meyer and so on in Daniel Loss's group, they have predicted this already more than 10 years ago. If you actually confine these holes in a kind of strong transverse confinement in a quasi one-dimensional structure, then what ends up happening is you get heavy hole light hole mixing. So these heavy holes and light holes, they have spins 3/2, plus minus 3/2 and plus minus 1/2, and you get mixing between these levels. And if you calculate this through in the theory, what that means is you end up getting a very strong so-called direct Rashba spin-orbit coupling. It's called direct Rashba because the traditional Rashba actually that was discovered by Emmanuel Rashba in the 80s, a long time ago, that traditional Rashba effect is actually kind of a higher order type of virtual transition. You have to go from the conduction band into the valence band back into the conduction band. And so these processes are suppressed with the band gap. And the band gap here is of order of an electron volt for these semiconductors. So this is a strong suppression, and it actually makes the usual Rashba effect a relatively weak type of spin-orbit coupling. Now, in contrast to that, the direct Rashba effect is suppressed not by the band gap, but actually by the confinement gap. So due to this strong transverse confinement, we get level quantization due to this transverse confinement, and this level splitting, these subbands, they're typically of order of 10 or 20 milli-electron volts. So it's about 2 orders of magnitude weaker than the band gap, and so this effect will be about 2 orders of magnitude stronger than the traditional Rashba type of effect. And so that's the goal here, to basically try to take advantage of this direct Rashba type of spin-orbit coupling. This could be very powerful. Actually, the prediction from the theorists with these references as shown on the left here would be that the G factor would depend on such parameters like the gate voltages, to confine these charges in this nanowire-like structure here. For example, here it's a silicon or germanium core with a shell that goes around it from another semiconductor material or an oxide. And this strained core then needs to have gates patterned over it. I'll show how that's done in just a few minutes. And that actually leads to the G factor having a strong dependence on the applied electric field. So the G factor is predicted to have this kind of gate voltage dependence. And together with that, the strength of the spin-orbit coupling, which is plotted on this lower figure here, would also depend on this electric field. At zero electric field, similar to the usual Rashba effect, the spin-orbit coupling would be vanishingly small, but then as you turn on the electric field, the strength of the spin-orbit coupling increases and increases, but it's non-monotonic. At some electric field, it would peak and then reduce again in strength for even larger electric field strengths. And so with the G factor, we can basically control the energy of the qubit. And with the strength of the spin-orbit coupling, we can control with an electric field the speed of the qubit, the velocity with which we can precess and rotate spins. And so that's the basic idea that we want to take advantage of for both this germanium silicon core shell nanowire qubits and also for the silicon FinFETs. And so in the remaining 20 minutes or so, I will tell you a little bit about the experiments in both of these platforms. So this work was published. We have a number of publications from 2018 until today, and also on the other platform, in addition to the theory papers, we have a number of publications that came out over the past few years. I would like to start now the experimental part by thanking, first of all, my team. They've done an excellent job, and it's great to work together with them. So to make these germanium silicon core shell nanowires, they're grown, first of all, by our collaborators. In this case, it was Eric Bakker's lab at the TU in Eindhoven. They grow these nanowires. What you see here is actually a TEM image, highly resolved and corrected. I think this figure is from this publication from Sonia Conesa-Boy from 2017. These nanowires are extremely skinny. They're very thin. They're only about 10 to 15 nanometers in width. You can see here the perfectly beautiful arrangement of the germanium atoms. And then the shell is made from silicon and is maybe another 2 to 3 nanometers in thickness around the germanium core. Of course, when you take these wires out of the growth chamber, then some of these silicon atoms will oxidize. There will be a thin, maybe half a nanometer to a nanometer layer of silicon oxide on the very outside of these wires. Now, nature is very generous with us because it provides for a natural band alignment that puts the Fermi energy inside the valence band. So we get basically for free, without having to add any sort of doping to these wires, we get the population of holes inside this nanowire. So all we need to do is we need to come from the outside, put gates over these nanowires. That's shown in the sketch here. So we pattern these gates 1, 2, 3, 4, 5. This is a top view down here. And actually, the students do an amazing job at making these very small structures. So these gates are about 20 nanometers in width, and they're about gaps of 30 nanometers between them. And this is quite difficult to achieve. It's at the limit of what we can do with our electron beam writer here at the institute. So then after writing this with the electron beam lithography, We grow an oxide over it with a micro manipulator. We put the nanowire on top of it. We contact it. Those are the contacts. There's a source and a drain contact here. And then we can actually drive a current through it. And by applying voltages to these individual gates here, we can start to deplete under the gates locally the population of holes and basically make it into a barrier. So we can make G1, G3, and G5 here, the pink ones, into barriers, and then we can localize just a few holes, maybe 10 holes inside the nanowire under gate 4 and gate 2. And that's the mode in which we operate here. So then what we use is basically a Pauli spin blockade effect to do the readout. So somehow, I mean, primarily we're measuring a current, an electrical current through this nanowire. This flows from the source to the drain, but we need to get the spin information. And there is a so-called Pauli spin blockade effect that was discovered 20 years ago, or even more, by Seigo Torucha and his co-workers in Tokyo. And here we're using this effect to basically turn spin information into charge information. So we have a multi-step pulse. We first initialize the quantum dot to have just the 2 holes in a kind of a singlet arrangement. Then we protect these spins from the microwave pulse so that we don't accidentally toss them out into the reservoirs. We turn on the microwaves for a short time. This is a microwave burst of typically nanosecond or a few nanosecond length. And if this microwave burst has succeeded in flipping one or the other of these spins, and if they go then into a triplet state, then the spin is no longer blockaded and it can actually produce a charge current. And if it hasn't flipped, then it's still in the blockaded singlet and it will not produce a charge current. So in this way we can read out. And what I told you already, by basically applying a microwave burst to one of these gates, in this particular experiment, we applied it to the leftmost gate. We're basically shaking the whole spin along the nanowire, along its axis, and this, due to the spin-orbit coupling and basically the relativistic physics, it produces a time-dependent magnetic field, which then basically does the spin resonance and manipulates the spins. So this is the resonance condition. Here we can see along these plots here, we plot the microwave frequency on the vertical axis and the magnetic field externally applied along the horizontal axis. And this V type of fingerprint shape that we see here is the resonance signature that we see. So that's when when the applied microwave frequency, the Larmor frequency, basically matches the Zeeman splitting of these spins. Now it turns out that these whole spins, they're in principle spin 3/2 systems, but as I showed before, due to this heavy hole light hole mixing, an effective spin 1/2 doublet emerges, and that's what we're driving here. So now if we start to actually change the length of this microwave burst, then we can see Rabi oscillations. And well, this is a typical chevron pattern where we change the magnetic field that we apply here. It's just around 180 millitesla, relatively small magnetic field. And the burst length is the vertical axis. And then the current basically here through this Pauli spin blockade mechanism tells us what the spin is. It's pointing, you know, up or down or up or down or up or down and so on and so forth. And so this allows us basically coherent control. Yeah, so is this really the mechanism of spin resonance that I was telling you about in the introduction? We can check it because this EDSR type of mechanism is expected to be proportional to the applied magnetic field and of course also to the microwave power, and we can check this. So here we plot the magnetic field and it seems to agree more or less with a linear behavior. And also when we turn up the microwave power, then the frequency of this Rabi oscillation goes up. And you see here, these are quite large frequencies, 200, 400 megahertz. Actually, if we drive it very hard, then we can achieve a Rabi frequency up to about 436 megahertz. This is quite fast. This means we effectively can almost flip the spin by pi or by 180 degrees in just around 1 nanosecond. So that's very fast. It's actually among the fastest semiconductor all electrical spins. There was a paper just now in 2022 in germanium hot wires, a related but a bit different a nanowire system that did it slightly faster, about 550 megahertz. So anyway, this shows that these spins are very fast, and this was one of the predictions of the theorists, that the spin-orbit coupling would actually be very strong. And by actually calibrating the microwave power and by measuring independently what the orbital level splitting is of the system, we can extract the spin-orbit length. This is this parameter here, spin-orbit length that we extracted is about 4 nanometers. And this is really surprisingly, strikingly small length. So the way this works is the spin-orbit length tells you what's the distance that the spin needs to travel in the semiconductor to execute rotation by 1 radian. And so in other words, the shorter this length is, the stronger the spin-orbit coupling becomes. And so just to give you a comparison, typically in what are otherwise considered materials with strong spin-orbit coupling, like indium arsenide, indium antimonide, the spin-orbit coupling length is typically 100 nanometers, maybe 50 nanometers. And so here we extracted 4 nanometers. This is a surprisingly strong type of spin-orbit coupling. Now, unfortunately, what I also need to mention is the coherence is not so exciting. It's a bit short. We've studied the decay of the Ramsey fringes, and this tells us that the T2 star, the so-called ensemble average, the coherence time, is about only around 10 nanoseconds. Now, that's what's still encouraging is that if we do an echo, so we make a slightly more complicated pulse, we don't only rotate down to the equator, we also do a rotation by 180 degrees around one of the axes, for example, X, and then we rotate back again by 90 degrees, then we can extend this coherence time to about 1/4 of a microsecond. And so this tells us that there are kind of sources of noise which are low frequency, which are slow compared to the time scale of our microwave pulses and manipulation pulses. So on the kind of microsecond and longer time scale, we have this noise somehow in our system. Now, is this charge noise, or is it nuclear spins, or are our microwave pulses not very well reaching our sample? These are a bit of open questions, but it's very encouraging that it's possible to make this much longer. In some other cases, this is not possible, but for our qubits here, we can make it 25 times longer than the bare T2 star. Also, if we modify the sequence with another pi x or pi y pulse by simply changing the time delay using our vector microwave sources, then we can actually demonstrate universal control of these qubits. So that means we can put the arrow of the spin onto any point in the block sphere as we like. And this is one of the key ingredients, of course, for quantum computing. So
sorry, Dominik.
Please go ahead.
So Jill is asking if would the coherence time increase if you could confine single holes?
That's an interesting question. In fact, for these experiments, we did not have single holes. We had something like 10 holes in each of the left and the right dot. And my guess would be, it's a bit hard to guess actually. So there's 2 effects. If you go to fewer holes, then you would have to push harder with these gates, and that would increase, for example, the energy scales, like the confinement energy scales, which could be advantageous. And from that, you could maybe naively guess that it could make the coherence better. However, if you go to the single hole regime, there is another effect, which is screening. So if you have many holes, there is more screening due to all the other holes, which are also present in the bubble of the quantum dot. And so maybe that would lead to a shorter coherence time if you had only one hole. and it's difficult for me to now estimate what that effect would be. We're nowadays working towards single hole experiments by using actually charge sensing rather than this Pauli spin blockade type of readout. And so we could possibly investigate this.
And
I'm now seeing there was more things in the chat. Oh, this is a different thing. Okay. Any other questions?
There is another question from so Herman, so who is asking, so if you could explain the reason why there is a charge noise.
This will be part of my remaining slides. I'm seeing I'm running a little bit out of time. We don't know. It could be that the charge noise is in the oxide that we put underneath the nanowire to separate it electrically from the gates. But actually, we have now improved the oxide and we still see the same type of coherence time. So I think we can now exclude the oxide. It could be on the shell of the silicon. There, I mentioned there is also an oxide. And this is actually kind of also a poor quality, just room temperature grown oxide. This could be the problem. But the short answer is we don't know. We have some suspicions and we're going to go after them. All right, so what's very particular about this qubit that this is the strong spin-orbit coupling makes it very flexible and tunable. So what we could show here by changing this voltage on the center gate just by a few tens of millivolts, we can actually tune the G factor from about 0.8 to about 1.2. That's a 50% change. That's a really big change of the G factor. And moreover, with the same kind of 30 millivolt change of this middle gate, VM, shown here in the red box, we can also change the Rabi frequency. That's the frequency with which these spins, precess from north to south pole on the Bloch sphere. And here it changes by about the factor of 7 from below 50 megahertz to above 200. Here I show some of these Rabi oscillations corresponding to a few different gate voltages. And so this is actually a kind of a new type of qubit where just by changing the gate voltage, we can change the operation speed and we can change the qubit energy. This was not demonstrated before, and here it's actually I think this is quite useful because you can go to a place where you can manipulate it fast or you can manipulate it slow, and then it's manipulated slow, then the coherence is better. So we measured also the coherence time as extracted from the decay of these Rabi oscillations, and it actually, unfortunately, it's inverse proportional here. So when we make the Rabis faster, then the coherence becomes weaker. And the number of oscillations that we see is more or less constant. It's around 5 or 10 or so of the wiggles that we can see in the Rabis. So this is basically a new type of qubit, and that's what we published in our Nature Nano paper about a year ago. So we can switch this qubit, and that's what this old steam ship switch is kind of indicating. We can switch this qubit from idle, that would be this left setting, where the Rabi frequency is a low number and the coherence is quite good, or we can switch it to manipulate or control, where the Rabi frequency is much faster. So I'm running out of time, and I think I will kind of skip through some of these other things that I was originally going to show. Let me actually stop the presentation mode. Yes?
Expand if you want. I mean, the time is extensive.
Oh, I'm very happy to hear that. Thanks very much, Christine. Maybe if I could talk 10 minutes or so about the other qubit, which I also am very excited about. I just used a lot of time to introduce the stuff first here. So I'm now switching to the FinFET qubit. So this is now not the nanowire, but this is actually a silicon transistor type of qubit. Here is a SEM picture that's taken at an angle. You actually see the fin. The fin is this purple structure that goes, from lower left to upper right here. Oh, I should switch back to the pointer. Here we go. And then we have a gate that goes over it. That's this plunger gate. We make them very small here, down to about 15 nanometers in gate length. That's this length along the fin here. And then there is a source and a drain contact. So this is really also a transistor. And in fact, in our first publication in 2018, we also demonstrated perfectly nice transistor operation of this object, of this device, for both electrons and holes. And so what we're doing now is we're basically turning this into a quantum dot. These gates are so small that it's possible to confine a single charge underneath the gate. And we can actually do a bit more lithography and put more gates around it to control it better. Let me also show you a cross section. If we do a cross section along the gate, that's then cutting across the fin, then we see that this is a 20 nanometer scale bar here. This is really zoomed in a lot here. You see that the tip of this fin is kind of smoothly rounded and is only about 10 nanometers in size. And then this material on the bottom here is basically the bulk silicon of the wafer. And we have etched this fin into the wafer with a kind of a top-down method in the dry edge. And then we grow a very high quality thermal oxide over it of just a few nanometers. This is about 7-8 nanometers in thickness. And then on top of that, we grow this type of gate structure, which is made from a very typical CMOS industrial gate process. This is titanium nitrate. For me, coming from research and not so much from industry, this was a very strange material. It's also a superconductor, but it acts like a metallic structure. You can apply gate voltages perfectly well, even if it's superconducting, it doesn't matter. And so that's what we have on top here. That kind of wraps around this fin. Note also that this fin, unlike some of the industrial fins, has a kind of small aspect ratio. Sometimes these fins are super tall. They're maybe 10 times taller than they're wide, but this is not the case here. Intentionally, we've chosen a fin of an aspect ratio of only about 1 here for our experiments. Okay, now we can also show you a cross section along the fin, and we do another lithography step, which is actually very elegant because it's a so-called self-aligned step. So we don't need to use any complicated alignment procedure, which has a finite precision here. We simply started from this center gate. That's the one that I showed you on the previous slide. We have these lead gates, L1 and L2, is shown in yellow. And then we fill in a little bit of ALD oxide. So this is atomic layer deposition. This nicely coats everything that goes around here. And this is the oxide that's grown here, about 4 to 5 nanometers of silicon oxide. And then we fill in these trenches with another atomic layer deposition, ALD step, which is again titanium nitrate. So these gates are also perfectly well aligned, and they're only a few 10 nanometer typically in length. You see the scale bar on the bottom left, and that gives us 2 additional gates. In addition to this gate 1, it gives us gate 2 and gate 3 to actually get more control over our Qubits device here. I should mention that these devices are fabricated at the IBM Binnig-Rohrer Nanotechnology Center, the BRNC, in Zurich, which is a kind of state-of-the-art mixed-use clean room, which is also used for exploratory type of research as we're doing it here. So the IBM folks, they're bringing a lot of expertise in the silicon technology from many years of working in this area. And we are actually capable of making very high quality devices as you otherwise would only get from typically industrial processes. Yet we're making these structure with e-beam lithography and all basically in-house at our partner here at IBM in a very fast and flexible process. So this is a very strong collaboration that we have now going since about 5 years with the IBM team. And basically by applying the appropriate gate voltages on these different gates, we use this gate on the left as a plunger gate and the gate on the right as well. The one in the middle is a barrier that we can then use to control how much tunneling is between the two holes. And then here we have basically a hole spin qubit 1 on the left and the hole spin qubit 2 on the right. And yeah, also here I would like to thank very much the excellent team that we're working with, both at the University of Basel, where we do the cryogenic measurements in our laboratories, and also the wonderful fabrication team at the IBM site, at the Nanotech Center, and also the theory support from our colleagues in theory, and of course our funding. And so here, let me actually emphasize, we see kind of nice triple points here. These bias triangles are a characteristic signature of double dot physics. So we have this left and this right quantum dot that gives this physics. And again, here for these experiments, we use the Pauli spin blockade effect, as mentioned before, to do the spin to charge conversion. And the manipulation pulse that we apply is exactly the same as before. But now actually, which is quite nice, we see the resonances of both qubits. So we see the qubit 1, which we draw here with a red hue going over it. And we also see qubit 2. And the reason we see it, I'm speculating slightly now, is that these gates, they're so close to each other and there is not so much metal between them. I mean, there's the barrier gate between P1 and the further spin, but it can kind of leak through the oxide and the semiconductor, and the qubit 2 can still see some of this field. So that's why we see the two resonances. For the nanowire qubits, there's quite a bit more metal around, and the gates are screened a bit better. So from the slopes of these, we can again get the G factors of these whole spins, and we can manipulate this extremely well. So here is a nice example of a Rabi oscillations. We've recorded this for about 2 microseconds. That's actually the longest time that we can do without losing the signal, because the currents become so small. The longer we make this manipulation time, the fewer repetitions we can do per second. And so, well, we're already down to a few femtoamps, so we really need to use here state-of-the-art current measurement equipment and so on to do this kind of measurements. But it's really amazing that we see here, I think it's about up to 40 oscillations without seeing any noticeable decay on this kind of Rabi oscillation plot here. So what this means here, if the current is 0, that means we're still in the singlet state, and that you can think of as a spin pointing down. And if we're here at the high current level, at this 40 femtoamp level, then the spin is pointing up. And here, as we're going through time, this is going, you know, from down back to up to down, and so on and so forth. So right, so from this we can extract a very good quality factor. That's basically how many Rabi oscillations we can see within the coherence time, and we think that's over 100. Unfortunately, we cannot measure it because our readout is not good enough for this. So I wanted to also briefly mention that I've mentioned already that it's very important for us to be able to measure such small currents, and actually ever since I came to Basel, I started developing kind of the electronics equipment that we need for our experiments, together with our wonderful electronics workshop with the head engineer of Michael Steinacher, who designs and develops these instruments in collaboration with our laboratory. We have a number of these instruments that we are now also making commercially available through our spin-off, which we started just a few years ago. So for example, also the gate voltages that we need to control the potential of the quantum dots, this needs to be very high resolution, very stable. We have ppm level stability, very low noise, and this kind of things we do. Also for the low temperatures, we need to be very careful to actually thermalize and get the nanostructures cooled well enough and protected from the disturbing kind of outside world influence. And for that, we built these great microwave filters. Okay, I want to kind of wrap up. I'm going to skip over a couple of things here. One big breakthrough, and this is what we recorded in our Nature Electronics paper, that came out in March this year, is that we can actually operate our qubits at up to 5 Kelvin. That's what's shown here. So we measure the decay of the Ramsey fringes, and this we were able to operate up to 5 Kelvin. And here you see the T2 star times that we can extract from such measurements, again color coded for qubit 1. and qubit 2. And at low temperatures, around 1.5 Kelvin, this goes up to 200, 300 nanoseconds. And even at 5 Kelvin, it's still above 50 nanoseconds. So this is quite amazing. Also, our readout, the Pauli spin blockade, is essentially limited by the singlet triplet splitting that we have there. And that can be very large. That can be up to 10, 20 Kelvin. But actually here we were limited, in fact, by the readout. At some point, it stopped giving us contrast. And so this is working, these qubits now are working up to 5 Kelvin and not anymore only at millikelvin temperature. So there were a number of groups that were recording this in 2020, a group at Delft and also in Sydney, they were recording similar results. They went up to 1 Kelvin and we now go even higher to 4 Kelvin. 4 Kelvin is a technologically important temperature to take note of because the cooling power just becomes enormously large once you can go to 4 Kelvin. Basically, this has to do with the boiling point of liquid helium. At atmosphere pressure, the boiling point is 4.2 Kelvin. And so simply by pumping at helium at this temperature, you can achieve excellent cooling power. In this case. So we can operate our qubits up to 5 Kelvin, and this allows in the future to kind of integrate our control electronics directly on chips. So in the future, we're actually collaborating also with partners who build kind of cryogenic CMOS control electronics chips that create these microwave pulses and control signals that we need so that we can kind of integrate a kind of a quantum part and a classical part even on the same chip. And we could all operate this then at 4 Kelvin. If this is possible from the quantum part of the chip, then this would be fantastic because we could produce a lot of cooling there. Okay, I'm now going to wrap up. I want to just give you one last very exciting development. We did a lot more research. It turns out this whole spin qubits, they have an amazing amount of anisotropy. So whether you apply the magnetic field in which direction depends a lot. So this is the XY plane, this is the ZX plane, ZY plane, and so on. And we can actually model and understand this in quite some detail. I will skip through all the formulas here now. And we have actually identified 2 different types of driving mechanisms. One mechanism is the one that I told you about. That's this so-called iso-Siemen EDSR, or just motional EDSR. And the other one is actually a G-factor modulation. If by applying gate voltages, even at microwave frequencies, you can actually change the G-factor, then this can also lead to so-called TMR. This is a G-factor G-tensor modulation resonance. So let me skip through that. What I want to show you is our 2-qubit gate, and then I'll stop. So basically, if you think about this level system, we have a spin on the left, that's the red one. We have a spin on the right, that's the blue one. And here on the right, I show you the level structure as a function of the detuning. So the detuning tells you what's the energy difference between the left and the right quantum well. At 0 detuning here, we have this transition, and the more we go to the left, then you start to actually slosh one of the spins, let's say the red one, onto the left quantum dot. So here we have this 1-1 regime where each of the quantum dots contains one hole. And on the right side here, we have this 0-2 regime. That's basically what we achieve here at the 0 detuning point. That's how 0 detuning is defined, where this 0-2 levels are coming in and becoming the ground state. And now if we turn on the exchange, that's basically tunneling between left and right spins. This leads to a so-called exchange coupling J. And when this J is turned on, then these levels, they start to anti-cross due to the tunneling. This is a traditional, typical level anti-crossing effect. It's just that we have quite a few levels here. And so then we have this up, 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 down, down, up, and down, down spins. And due to the exchange, they start to curve here and start to give us this kind of nice and complicated level structure. And actually, that's what we went to look for. And after we changed the voltage on the barrier, if this voltage is too too strong that this doesn't allow tunneling between the two dots, or not enough tunneling, then this exchange becomes very small. It's actually quadratic in the tunneling. So that's why you can get current, but you can still have a very small J. And that's the regime that we first operated in. But if we make this large enough, then we can see the J, and that's a picture of it. So we see this energy of the qubit transitions that corresponds to these transitions shown with the arrows. And here at the left side, the kind of two blue arrows are almost degenerate, and the red arrows as well. And as we're tilting it more here towards zero detuning, we start to get a splitting, which is the exchange splitting. So each of these goes into two lines, and then the light blue one is, for example, this transition from up to up down. And the other one, this extreme one here, the red one, would be then from up down to down down. So we can actually resolve these different transitions very nicely. And now if we change the voltage on the barrier gate, we can actually get excellent control. On the one hand, over the tunneling. So this is the tunneling rate between left and right dots in gigahertz that we extract from a model based on the size of the exchange, which we measure here in this data. And also the exchange, we can change by almost a factor of 100 just by changing this gate voltage here over maybe 50 or 60 millivolts. So we can actually tune this 2-qubit exchange from several hundred megahertz down to just a few megahertz as shown on this plot. And that then also leads me to the final slide. We can also show basically a very fast 2-qubit operation here. So by doing an adiabatic ramp slow here, we can stay in this state rather than transitioning over. And then we populate only this state, and then we see only this light blue and the dark red transition. And then those are conditional on the populations. So here, for example, we do two different pulses at two different frequencies, corresponding the light blue one to the blue arrow frequency and this one to the red one. And then, well, if we don't pulse the first one, then we see this thing oscillate. But if we do pulse it for about 35 or so nanoseconds here, then we don't see anymore the other qubit oscillate. So depending on what state qubit 1 is in, we either see or don't see the Rabi oscillations of the other qubit. That's a so-called controlled X gate. It's one of the standard 2-qubit gates, which we have here realized. Okay, so let me put my summary up. I will not read through it, but if you like to go through it, you're very welcome to do so. And I will stop here now. And I hope I still leave a little bit of time for more discussion and questions. So thanks again for the invitation. It's great to give this talk here. And thanks very much to all the listeners for your patience. Thanks very much.
Thank you very much, Dominik. It was very comprehensible and very exciting to see the progress that we can reach nowadays. So do we have questions from the audience in addition to those that we had earlier? And feel free to write them if you want, if you prefer, or just to raise your hand if you want to speak.
So I have now opened the Q&A, so I can look at that, but people can also speak.
There is a question, yeah, in the Q&A.
Thank you. Let me read this. Thank you for explaining your incredible research and achievements. Is it possible to set up arrangements, except for technical difficulties, by other gate materials like graphene in the form of quantum dots or nanowires, nanoribbons, used to achieve stronger spin-orbit coupling? What about strongly correlated electron materials? Does this help improve the time length of Rabi oscillations? Very interesting question. Thanks a lot. So yeah, I mean, the world has a huge zoo of different materials, and of course graphene is a very exciting material. We have seen wonderful research, for example, with these twisted bilayer type of structures, and people have now started using graphene, in particular in bilayer graphene. I've seen very nice T1 measurements, so people are going in the direction of making qubits out of graphene. The T1 times there, I would say they were very encouraging. I seem to remember up to 200 microseconds for a T1. that's a nice first step. I think what would need to be done now is to make a qubit out of it, basically apply these kinds of pulses and have a readout scheme, and then see what kind of the coherence times are. And this is not known. We don't know this yet. So this is an open question. And I think it's a research program. Unfortunately, we're so busy with our semiconductors that we won't be able to add the graphene, program to our cryostats, but I think it would be interesting. Let me just say, actually, in particular, graphene, it has very weak spin-orbit coupling, because basically in these carbon nanostructures, it would come from the curvature, but graphene is essentially flat, right? It's kind of 2D flat material. There's not much curvature. In carbon nanotubes, you would have strong spin-orbit coupling. You could use the same tricks that I was showing here to manipulate the spins. You could use them in carbon nanotubes. In graphene, these would probably not work. I don't know, I think. In ribbons, that's a different story. That's an interesting question. What about strongly correlated electron materials? Yeah, I have no idea. I think my very, very naive and maybe silly guess would be that the strongly correlated means there's very strong interactions between the charge carriers in these materials. And I think these would intrinsically lead to very short coherences, but I could be wrong. I don't know. I'm not actually aware of any qubits made out of like a strongly correlated material. I'm probably just not aware of it, but I can't remember seeing such experiments.
I think it was really complete. So Peyman, if you want to maybe share as well with your own study, anything that could be correlated to that, you can speak. Otherwise, so we will investigate as well with maybe the team who were speaking directly as well from Singapore, working on the graphene, if they have as well any type of study in that direction. So thanks for this question. So do we have maybe from as well our colleague? So from Joe or Marie-Lena, any question?
I have a question. Thank you, Dominik, for your nice talk. You showed us different platforms, but in terms of integration with the current technology, what do you think is the most promising platform for, I don't know, for our phones, for our computer, in terms of fabrication?
In terms of using existing nanofabrication facility, it's clear that the FinFET is basically the winner. I mean, FinFET transistors, you can today already buy, billions of, you probably have them in your, gadgets, in your notebooks and so on. So they are already very highly integrated. They're just not quantum yet. So now we have to find out how to put the quantum, in that transistor. That's what we're kind of trying to do on the FinFET project. With the nanowires, right now we're placing them with a micromanipulator on the substrate, but we have within our research network here in Switzerland, we have grower groups who are studying how to actually do top-down patterning and grow entire networks exactly where you want them and how you want them with such nanowires. Now, this is a materials development project right now. The quality of the nanowires is not there yet to make qubits out of it, but this will come. I think it's a question of another year or maybe some time. And then this will also be very scalable. Then it's also quite possible to do that. And there are some clear advantages also of the nanowires. I mean, the spin-orbit coupling there is even stronger than it is in the FinFETs. And for example, this makes it possible. We haven't shown this yet, but I think the theorists predict that it should be very easy to couple these spins to a photon. You do spin-photon coupling. Basically, you can couple directly through the spin-orbit coupling the whole spin to the photon, and this would be very useful. You could basically place many nanowire qubits into a resonator, and each one of them you could individually by changing a gate voltage, you can decide whether or not it's on resonance with the resonator, then it couples, or whether it's off resonance, then it doesn't couple. And so that's also a very, very nice flexibility that we would get.
Thank you, Dominik.
So maybe a short, oh, Joe, go ahead.
All right. Yeah, thanks a lot. That was really fascinating. I had a question about the temperature limit. I mean, so far you've gotten up to 4 Kelvin. Is there a limit to how far up in temperature you can go? And even at 4 Kelvin, is there an issue with stability, or is that temperature stability not a real problem for the operation of these FinFETs?
Yeah, that's a good question. Thanks, Joe. We are right now mainly limited by the readout. So the physics of the Pauli spin blockade is generally well known, but in this particular case, what's limiting us for the readout is not completely obvious, and I think it's simply the energy splitting between the 0,2 and 1,1 states, which is probably about a few millielectron volts. You know, a millielectron volt corresponds to about 11-12 Kelvin, and so at some point when that temperature is reaching the splitting, then you start to kind of destroy the Pauli spin blockade effect. So the readout doesn't work anymore. And I think that's what's limiting us presently at this level of 5 Kelvin. Eventually, when you go to even higher temperatures, let's say 50 Kelvin or so, and also the spin coherence will become a problem. But so far it was the readout. And I'm not sure how to push it. I mean, some groups are actually reading out in a different way. And this is even more temperature sensitive. You can do so-called Elserman readouts. There you're making the difference in energy between spin up and spin down so large that it exceeds temperature. And then you can do the readout such that if it's in the excited spin state, the charge tunnels out and produces a current. And if it's in the ground spin state, it does not tunnel out and it does not produce the current. So you directly convert via the Zeeman splitting. Being larger than temperature, you convert spin to charge. And of course, for that, then if you want to go to 5 Kelvin, it becomes extremely difficult because you need to run at, I don't know, 200 gigahertz or something. I mean, we spend a lot of money on our microwave equipment, but it all stops at 13 or 20 gigahertz. We don't need to go to even higher frequencies. That would be too expensive for us to run. So the readout is currently the problem.
Okay, thanks. Yeah.
Indeed, it was the same question as well. Similar as well question by the fact that if you are running as well at higher temperature, then you don't benefit as well from the stability. So you may have as well vibration or kind of more difficulty as well on the experimental setup.
Absolutely, yeah. Vibrations. I mean, we have different types of cryostats, but nowadays it's very convenient and also popular to work with these pulse tube cryostats because they don't require liquid helium transfer, and you know, it makes kind of the running economic, because otherwise you have to keep paying for liquid helium every week. With the pulse tube, you have to keep paying for electricity, but normally the electricity is covered by our institutions. It doesn't go on our research budget, at least so far. But so the pulse tube cryostats suffer from a lot of vibrations. So basically, it's like a hammer hitting your experiment at 1.4 hertz, you know, all the time. I mean, every day, every minute. It causes a lot of electrical problems. I mean, we're not trying to run a microscope here, which would be even harder. Some people do that and they also succeed, but just for the electrical signals, we have this 1.4 hertz comb all over the place, and it's a hassle to deal with that. So sometimes we actually enjoy the quietness and beauty of our liquid helium cryostats, even though we have to pay for the helium.
Yeah, thanks a lot. And maybe just a very last question. You mentioned initially when you were introducing the supraconducting versus as well the silicon different research. So what do you think future will go? It's it looks at with the silicon, so there will be more feasibility, or does it cost more or less? Is it like in implementation as well, some advantage?
This is the million or maybe billion-dollar question. Of course, I don't know the answer to that. I put my eggs in the basket of the semiconductor spin qubits, as you have seen. I mean, I think ultimately, if maybe the superconducting qubits can be made smaller, that's an open question. But if not, I really don't see how they can integrate, 1 billion qubits on a chip, because that chip would have to be the size of the city of, I don't know, Geneva or Basel or someplace. Huge. I mean, it's impossible, and you have to cool it below the superconducting transition temperature by a factor of 10 or so. So I don't see that. I mean, the problem with the semiconductors is it's incredibly hard to make these kind of transistors. The only reason we succeed now is because we have the experience of 30 years of research that we're building on. So a colleague of mine once made this analogy. I mean, with the ions or with the superconductors, these are easier to build, but you're basically trying to build a fancy bicycle, But the goal is to fly to the moon, and it's difficult to imagine how a bicycle will fly there. I mean, with the spins, I believe we're trying to build a rocket. It's just very hard, but eventually, hopefully, it will take off.
Very good. And we have another question as well from Adelaide. So on the question and answer. So why not working with the QDevil company? So I don't know if you know them. So they're expert in qubit control.
Yes, no, I know them very well. It's an excellent company. They're also a spin-off from my colleague Ferdinand Qubits and his lab and Charlie Marcus's lab at Copenhagen. Well, we used to use some of their instruments actually, but some of the things that we do are also complementary. For example, the pre-amplifiers, they are made not by QDevil.
Very good. So any last question? Oh, we thank Dominik once again. So for this, it raised a lot of questions, and I think the future is promising. So thanks to such research. So we have to stay tuned as well. And we see Luisa is connecting, and she was not here at the beginning, but so
no, I was here since the very beginning.
Where? So from the space, what do you think? Can we fly a bike to the moon? Luisa.
Do you want my opinion? Probably yes, in the future, yes.
Yeah, we see that science fiction becomes reality now, and not only virtual reality, but real.
No, but if we think back, I mean, the progress of science is such that one can really imagine, have no limits in imagination.
Exactly. So thanks again for this wonderful presentation. So I think that we will certainly have some follow-up at some point with so the research with IBM. I think it was as well a very good way to see how industry can pick up, and we need as well the investment to be able to go even faster to the moon. Okay, so I will maybe simply come to the conclusion as well with the introduction of the next presentation. So I will share my last slide here by showing that next month, so we will have the opportunity to listen to a group of very influencing people who change a bit and certainly get the Sesame to become. So that was since 1997, and we will have in the honor of so Herman Winnick, the possibility to gather so Erwin Schopper together with Chris Level-Smith and Rolf Heuer Zafra Lerman, Zera Sayer, Tord Ekeloff, and Giorgio Marcaritondo, who both, Tord and Giorgio, were as well with Ada as the first organizer as well of this conference, which kickstarted the Sesame. So the origin of the Sesame is expected on the 28th of July at 10 EDT, so the time in the US, but then still our 4 p.m. in Europe. So you are all welcome to attend, and as well, during your vacation, send us as well some comments, some questions, and feel free to participate and to share this information so with your colleague. So we are looking forward for this coming presentation as well. And we can otherwise so finish on this note, a happy note, hoping that indeed science diplomacy and science for peace will help. Also the price of the electricity in some sense, if we extrapolate. But indeed, thanks you very much, Dominik. So that was a great presentation. So, and good luck for all the research. Thank you. Everyone.
Thanks very much. It was great to be here. Thanks a lot.
Bye.
Thanks.
Bye.
Bye.